everyone. Welcome to the second lecture on probability and statistics. What did we discuss in the last lecture? आपको याद है? क्या डिस्कस हुआ? काफी कुछ डिस्कस हुआ. Yeah? Okay. So do you recall anything we talked about? Let's say probability. What was it? Lack of knowledge. Okay. So we talked about that. Your height is something certain for you. Yes. But the height of the next student coming in, uncertain. That was the lack of knowledge. So what did we do with the lack of knowledge? We realized that in most situations it's not absolute. You still know something about the uncertain event. Yeah? And then we can try to collect information, collect statistics, and make good guesses, guesstimate, right? Based on that information. Instead of saying, okay, I'm not sure. Yeah, I know, I won't be able to tell you the height of the next person. I cannot tell you, right? At this point. But that should not stop me from designing doors for humans. Right? I should be able to work with some sort of statistics to tell. Your mobile phones have these, many of them have image face recognition, yes? But your face varies from time to time, little bit, yes? The features change a bit when you wake up, when you've been running, if it is dark, yeah? But your mobile, in most cases, if the vendor is good, I don't know what you get from China, but the good ones, they can still recognize you. Within the variations, the algorithm behind it is still able to recognize that it is you, right? Now, the trick is it should not consider someone who looks much like you to be you while still accepting variations in your look, right? That is the challenge. So, from uncertainty, we can still extract some information that works with some sort of, let's say, certainty, and that's what we talked about last time a little bit, and we were assigning probabilities, right? We thought, okay, let us work with how can we talk about uncertain events and then assign them probabilities. One example that we see many times here is rolling a die. Yes? The outcome of that is what? Uncertain. Compared to that, the outcome of x plus 2 equals 0 is not uncertain. Right? It's always x is minus 2. That is, you're used to the idea of certain events, certain things. Yes? But uncertainty, in this case, rolling a die, that's our experiment. The outcome is uncertain. You roll the die, you throw the die, and what you get, we want to assign some probabilities to those outcomes. So, how did we do it? We talked about a few important steps involved in doing that. So, let's see. What were the steps we talked about? I said there are 5 steps in assigning probabilities. What's the first one? Your setup. You cannot assign probabilities to everything. Yes, generally. You have to decide, what am I working with? Is it the probability of a certain set of bulbs blowing out in one lecture hall? Is it the probability of a machinery failing in a certain factory? Is it the probability of a person's facial features looking different from what is already the samples that are already recorded? So you have to decide your setup, and this thing, for at least bookish purposes, we call the experiment. Yeah. So we have the size. first thing was setup or experiment. That has to be very clear. What is your setup? Okay. So in rolling the die, what is the setup? You roll a die, a fair die, so it has 1, 2, 3, 4, 5, 6 written on it, and you observe the number that shows up. Yeah? Okay. What was next? The event is uncertain, but we say, okay, what is the world of possibilities in this experiment? The set of possibilities. For that, we quickly review some sets operations because we will need that. So, what is the world of opportunities or possibilities here? Is the set, universal set or sample space, right? What's the sample space in this experiment? What can you see? 1, 2, 3, 4, 5, 6. That is your sample space. So what you can observe is 1, 2, 3, 4, 5, or 6. Yes. You cannot have. Get used to this. You cannot have a 7 on the die. Yes, you cannot have 1.5. So this is your sample space. What was the third thing? All of this is what? Our first module. Remember I said the course is in 5 modules. The first one is talking about uncertainties mathematically. So this is what we are doing. Assigning probabilities, talking about them mathematically. Define your experiment, set up your sample space. This is mathematics. Yes, you set it up now exactly. This is the set of possibilities. Third thing was what? Define your event. In probability theory, event is what? Something that you are interested in studying. An outcome of the experiment. Experiment is key outcome or something. But at one point, which one are you interested in? The bulb blowing out. That is the event. Right? Let's say. In this case, event could be it is outcome of interest at this point. Could be multiple things, that's fine, but whatever events you want to define. So in this case, let's say I could say event is, it shows even number. That's an event. Let's say I want to, and we could write it as a, let's say event A. And now this is written generally, but for this sample space, what should A be? 2, 4, 6. Yes? That is how it will show an even number. Okay. The fourth one is, as I mentioned, now you try to assign the probability. One way that we often use is to use set measures. Size of the, so the probability, this one we will call sample space S. Yes. So probability of A is the size of A divided by size of S. Size here means how many elements in there from sets. You could also say number of ways A can happen divided by number of total possibilities. But since you have written those as sets, so for your case, A has a, how many values does A have? 3. Yes. And S has 6. So 3 by 6. What's the probability that an even number shows? 1 by 2. 3 by 6 is 1 by 2, which you also know intuitively. The only reason I'm developing is that actually this is the thing that just expands into higher problems. Right? The concept is here. Now there is an assumption in this definition that I briefly mentioned last time, but we will look at that in more detail today also. The assumption is that when you're counting, if you're doing the size thing, if you're counting the elements, then each one has to be equally likely, has to have the same chance of happening. Okay, so in this case, is that satisfied? If you roll a die, is it more likely that 2 will show more than 3 times or more than 3? Is it more likely, or are they all equally likely? What should you expect? Is it a fair? If it is a fair, there's no trick in there. Yes, then they should show up with equal chances, equal probabilities. So all of these are equally likely. Let's put it on silent. So probability that 1 shows up, by the way, is what? By this formula also, and by your guess, what is it? 1 by 6. What's the probability that 2 shows up? 1 by 6. 3, 1. Each of them has probability 1 by 6. They are equally likely. That's why we are able to use this simple counting procedure. Okay? So, okay. Now, you assigned the probability. You found in this case it was 3 by 6, and that is half. 50% of the time you should see even numbers. Yes, makes sense. No magic about it. But it's this process, the 5-step process, that I want you to see. Where is the 5th step? I mentioned that briefly, but we didn't cover it in detail. Yeah? What was it? Sorry? Assigned probabilities must make sense. Okay? So, this is a, let's say, sense check or something. Sanity check, sometimes we call that. So, we will also look at this. And the thing that helps us check the sense, do you know what's an axiom? AXIOM. Right. Axiom in mathematics is, or in logic also, is a statement that you cannot prove in that field. So in mathematics, if there is an axiom, you cannot prove that axiom using mathematics. You just assume that is true. So if I say that x equals 1, does x always, or if I say 1 equals 1, for example, you have to accept that. Right? From our universe, we know that this is how things are. Yeah? So axioms are things you don't prove. They are the very foundation of any logical argument. So mathematics is also an axiomatic system. It has its axioms. Maybe you have studied some, maybe you haven't, but you should get familiar. Just Google it, try to read up. It's very useful for you guys, engineers, scientists. You should understand that a lot of what we do in the world, in sciences also, is based on axioms. Okay? And those axioms you cannot do. That is the answer. Anyway, so the sense check will be based on 3 axioms. Axioms, that is statements that we feel probability should satisfy. Okay? We won't be proving them. We can't prove them. And they were defined by Kolmogorov, Russian mathematics. You know when? Mathematics is a Purana field. Yes? But you know, probability is a baby compared to mathematics. Mathematics is like this old man, 90 years old. If math is 90 years old, probability is maybe just infant. Okay? इसके axioms लिखे गए हैं 1930s. Okay? Pascal was among 1800s were the first people who started thinking of this uncertainty in mathematics. ज़्यादा पुराना तो नहीं, मैथ तो 3-4,000-5,000 साल पुराने theorems भी मौजूद हैं, prime numbers भी. But compared to that, probability is a very new field. Okay? And before now, before recent developments of early 1900s, it was mostly, Cambridge and was there. Now it has become a critical component of our work. Okay? Because now we are able to collect a lot of data. You know, आपका chat GPT है, क्या magic कर रहा है? The thing is, now it has access to so much data right? Billions and trillions of bytes of data आप उसको throw before you had to show an algorithm maybe 10 pictures of cats, you had to take those pictures. अभी आप खुद गूगल करें तो आपको सारा दिन cats की तस्वीरें आती रहेगी, कितना डेटा है. All of that you can throw at an algorithm and tell you, okay, these are the variations in a cat. Now learn it. This is a cat and this is not a cat. Yes? So you can create that. So anyway, that's a digression. Kolmogorov's axioms. I won't call them this again because you guys get scared. We'll just call them the sense check. They will tell us, okay, this probability assignment makes sense or not. Okay. So also another thing we will talk about today is this. So far we have assigned probabilities to single events. Yes? Event kya tha hamara? Shows even number. That's one event. Yeah? But today we will also expand this thing. We will talk about combinations of events. Okay? We will try to see, okay, it's an even number and less than 5. Okay? In this case. Yeah? So we will add, we will go to from single event, single uncertain or random. From now on I will use the word random also. What's a random event? Something whose outcome depends on an uncertain experiment. Okay, if you're not sure. The sun coming out or setting today is a आज रात को सूरज नीचे जाएगा. Axioms तो यही है. That's an axiom by the way. You can't prove it. हो सकता है ना जाए, right? But axiom is that it will. The universe hasn't changed that. So it's a certain event. Those kind of events from now on, all of that we are studying will fall in the category of deterministic. Okay? So those were whatever you talked about before today was deterministic. And in this course we are going towards what? Random, uncertain. So these are the words that we use or the terms we use. So we went from fixed event, certain event. What is your height? You know it, certain event. What's the height of the next person coming? Uncertain event. So we went from certain events to uncertain events. That is, we went from deterministic to random events. So today we will also go from deterministic variables to random variables. Okay? Event है, फिर एक variables. We will come to that. But we will start with expanding on this one. Event. Yeah. So from single event to multiple events. We are often interested in talking about probabilities of multiple events. So one thought how to do this was laser and so let's go to that. Multiple events, talk about multiple events. One thing I've already talked to you about is, did you notice that in the die rolling thing we mentioned, probability that, I'll just shorten it like this, probability that a 1 shows is what? Is 1 by 6, you know, yeah. So probability that a 2 shows, they're all the same, yes? That was 1 by 6. They all have the same probability. So first thing, this is important. I've already mentioned this. Such events that have the same likelihood of occurring are called equally likely. Okay, that is the vocabulary you need to learn. Okay, experiment, event, random, deterministic, equally likely. ये आपकी language build हो रही है in probability theory, right? So focus on the terms. Try to get to the bottom of the terms and try to absorb those terms, make them part of your vocabulary, right? Otherwise क्या होगा अगर आप इन terms को absorb नहीं करेंगे साथ साथ, you don't make a list of them and try to get really familiar with them. After a few lectures, you will feel I'm speaking Greek. Few terms ही अलग हो जाएंगे, or maybe I'm teaching you biology. Totally terms different लगेंगी आपको. So start absorbing, start noting the important terms, the language, the vocabulary of this course. So that is equally likely. Now there are two ways that we come to this conclusion that events are equally likely. One is intuition or experience. Roll a die. You didn't calculate the probabilities. I just showed you the formula, but you didn't use that before. You know intuitively that every digit on the die has equal chances of happening, right? So in most cases, the assumption of equally likely is a belief or something based on our previous experience. Yeah. In other situations, which are more complicated, we end up doing lots of calculations and we find that, okay, probability of event A and probability of event B came out to be exactly the same. Then you say they are equally likely. Sometimes we start with the assumption that they are equally likely, and sometimes we calculate and then we come to the conclusion, yeah, okay, it shows that they are equally likely. So it changes with the problem at hand. Okay, that was again. Now why is this multiple events? Because now you're comparing events, aren't you? Yeah, so you started comparing events. Good. Let's see another example here. Let's say I have 1, 2, 3, 4, 5, 6 rolling a die. Yes, and I define event A as this. ये नजर आता है ये वाला ना, right? Okay. And I define event B as this, and of course the whole thing is what? Sample space for this experiment. Every experiment has its own sample space. If you throw two dice, sample space changes, right? Differently. So what is this? Event A is what? Odd number shows. Yeah. Event B is even number shows. Okay. So can anybody tell me what is the probability that A and B occur at the same time? Remember, you mentioned and is for us is intersection. Yeah, B, A, and B. What do we mean by and B? That A happens and B happens. They both happen. What's the likelihood of this? As I said, yes. So as I said, we are going now from single events to multiple events. Sometimes we compare them, sometimes we try their intersection, sometimes we try their union, sometimes we try their complement. So what's the probability of A and B, as you said? 0. Yes, logically you can already see it makes sense that it is 0. Yeah. So events, what does this say when the probability is 0? What are you saying? If you say it in words, what are you saying? When you say that the probability A and B is 0, they are mutually exclusive. That's the term I want to come to. Yes, but you are saying that they cannot happen at the same time. Yes. So events that cannot happen at the same time, from now on, what we call them? Mutually exclusive. And if you see the sets of such events are disjoint. What are disjoint sets? That have no common elements, right? Are A and B disjoint? Yes, no common element, right? So this is what we call mutually exclusive. And you don't need to apply probability theory to know that number cannot be even and odd at the same time. But here, in this case, I just want to show you. We will see more advanced examples, of course, later. But and we will also see, okay, this was the case when probability of two events happening at the same time is 0. But what if they are not mutually exclusive? Yeah? Then how do you calculate this? We will come to this later today. But for now, I just want you to focus on mutually exclusive. So events can be equally likely. They can be sometimes mutually exclusive. And what else can they do? We will see that with time. Right. Now, sometimes we are interested in seeing, okay, I want to say, okay, what's the chance that this happens or that happens? So I want to see, okay, one of the two events happens. What's the chance of that? Yes. Here I am saying both of them happen. Yeah? But sometimes we are interested in looking at, okay, one of the events happens, what are the chances of that? So let's see. For that, we have probability A or B. What is it saying? What is the chances that A happens or B happens? Now, in the previous example that I have here, what was A? Odd numbers. Yeah, B was even. So, what's the probability of A or B? 1. Yes? Why? We're saying, what's the likelihood that the die shows an even number or it shows an odd number? Of course, it will either show an even number or an odd number. So it is 1 in this case. But the concept is this, and we in sets, this is what? Union. Yes? Union B. Probability A union B is when you say, okay, what's the chances that this happens, A happens, or B happens? Yeah. So it is less restrictive. It's more inclusive. या ये हो जाए दोनों acceptable. जबकि and क्या कहते हैं intersection says both should happen at the same time. Yeah. So A union B in this case is of course 1. But what about this case? Let's make it a bit more interesting and say, okay, we have 1, 2, 3, 4, 5, 6. Again, I'm talking about rolling a die. And event A is, let's say, event A is that one of these numbers shows, okay, 1, 3 or 4. इसका color change होता है क्या? And B is this. Let's see now. पिछला तो आसान था ना, तो आपने फौरन जवाब दिया. Yeah. Now, what is the probability that A or B happens? 1 by 4. 1 by 4. 4 by 6. 4 by 6. So we're getting different numbers. Let's see. We will go back to 10. So let me write out the general formulation and then we will discuss it. So we have a, of course in this case you will see apply this also, but let's see. We have a formula that helps us find this kind of situations, and this is what it is. What is it saying? This is a very general formula. It applies to all unions. Probability of A union or B is what? Probability A plus probability B minus probability A intersection B. Okay. Now, can somebody tell me why the minus there? दो दफा काउंट हुआ, तो आपने क्या किया उसको? एक दफा निकाल दिया, बैलेंस हो गया, right? Because they had a common element. By the way, are A and B mutually exclusive in this example? No. Yes? Are A and B equally likely? Just for your practice. No, right? A is more likely. You can see what happened there. Right. So, सबको समझ आ गया? There is a common thing here, 4. When you take probability A, you count 4 among your possibilities of allowed possibility. When you take probability B, you again count 4 among your possibilities because it was common. Okay? So you ended up counting this possibility twice. So once you have to remove it. How do you know what you counted twice? Whatever was common, कुछ और तो नहीं count उसका twice. Remove the common. A intersection B is the common part. So you removed it and you notice that this is what happens. I like to see it also as what it's really doing is also, by the way, if there were no common parts, what will happen? We already discussed that, right? If there were no common parts, they would be mutually exclusive, and we saw that for mutually exclusive events, intersection is probability of A intersection B is 0. So if we automate it, it's a very general formula. It doesn't care if there is common points, they will be removed once. If there are no common points, this guy itself will become 0, as we already said, because they are mutually exclusive. So the way I like to look at it is this. I'll take this away. Laser right. So what I'd like to think of it is doing this. What it's doing is basically saying, okay, I will give you probability of A union B like this. I will say it's the probability of A minus probability of A intersection B plus probability of B. Okay. This is what it's, in a way, this is what it's doing. So what is A minus A intersection B? What it does is basically, if I can, there is more space. Would you agree that A minus A intersection B is this? इसीलिए हमने last time थोड़ा सा revise किया था sets. You agree with that or no? A is 1, 3, 4. A intersection B is 4. So A minus A intersection B remove 4 from it. We're left with this. So notice this formula that we saw can also be seen like this. Right? I just moved the minus in here. But notice what it does is it makes these two groups mutually exclusive. Up to common right? Yes? So since they are mutually exclusive, the intersection part is not needed and you can simply do a sum here. Yes? Another way to look at it is to say it's doing probability B minus probability of A intersection B. Okay? So this is B. In the other case, if it is B minus A intersection B, then it is doing like this. It says, okay, A will remain as it is. So this is A. I will take the probability of A plus I will probability of B minus probability of A intersection B. Yeah. So this is 4 and this is now 6. This is A. What is this? B minus A intersection B. Okay? This one, B minus A intersection B. Again, are these mutually exclusive or not? Disjoint है. Yeah? So there are many ways of making intuitive sense of this formula. Okay? So back to the union formula. What was it? Probability of A union B is probability A plus probability B minus probability A intersection B. If A and B are mutually exclusive, this will disappear. If they are not mutually exclusive, whatever was common between them and was counted twice thereof would be removed once, and your formula would be, or your calculation would be correct. Now you can check the answers you were giving me. You can check if what of those or which of those were right. So what did we talk about? Equally likely, yes. Then mutually exclusive, and then we looked at and events occurring at the same time, events or one of them occurring. Now we see the idea of not. Remember A prime, yes, or the complement. So what is that? Let's see. We showed that if this is your universal set or sample space, and this is A in here, then what's the area that is not in A is A prime. Yes? And by their very nature, A union A prime is always, so A prime is this area, the shaded one, yeah, not the A inside. A union A prime is what? S. Yes? So that is understood. Okay. So the prime is A union A prime. So can anybody tell me what is the probability of A union A prime? What? It is? One answer is 1. Do you agree or?
Yes.
You agree? That's good. Why is it 1? All possibilities are covered. Yes? So since all possibilities are covered, together they should be 100%. Kuch to hoga. If this is truly your sample space, yes, then something among them has to happen, and A and A prime cover everything. So you're saying either this happens or it doesn't happen within this sample space, so they are 1. Now, if I want to expand this, how shall I write it with the formula that we just saw previously? Probability of A union B. Now B is what in this case? A prime. So what is that? Probability A plus
Probability of
A prime minus, and what is this? 0. By their nature, their union makes sample space, but their intersection is an empty set. Yeah? 0 to numbers of that. Its intersection is an empty set, so the probability of the empty set of course will be 0. So what are we saying then? This is equal to 1. We just saw that. Yeah? But then can I say that the probability of the prime of an event is in fact 1 minus probability of the event. Agreed? This is a formula basically. And you know how it comes out. Yeah? So equilikely, mutually exclusive, together happening at the same sign, that is concurrent. one of them happening, and now we have seen also the probability of the complement. Probability of an event not happening is 1 minus probability of the event happening. And you may say, oh yeah, this feels silly, but they come in handy. All these tools, they come in handy when you're dealing with bigger problems. Yeah. So in many cases, this might be hard to calculate originally, but conceptually this might be very easy to calculate. So just get this 1 minus this, and you're done. Okay. So we will see that also the probability of the complement. Right. With that, we are done with the thing I was talking about, the original multiple events. But now let's talk about the sense of the problem. We've been assigning probabilities now, right? Different ways. We started with some basic experiments, then we went into functions of probability. Now, what should an assigned probability, what logically it should follow? कोई आपका guess है? Let's say I say probability of an event A is 10. Does that make sense? No. Right? The way we are defining probabilities, कोई logical क्या आप कहते हैं? What kind of sense it should make? The value you get. Or any कोई इसी तरह भी आपने calculate किया. Whatever the way, what the value you get here, if I say that the probability of A equals X, then this X, इस पे क्या शर्त है?
Less than 1.
Less than 1 or equal to 1 भी हो सकता है?
Less than
Less or equal हो सकता है? Yes, you could say A could be S. That is 1. Okay. So it should not be more than 1. What else?
greater or equal to 0.
Probability cannot be negative, right? So we are saying one logical sense it should make is that the assigned probability should be greater or equal to 0, less or equal to 1. When it's 0, the event is impossible. Yeah, but negative doesn't make sense in terms of probabilities. Yeah? Okay, that's actually one of the axioms. What else? So you have, let's say you have this experiment where you were assigning probabilities to rolling die. Yes? By the way, when we assign probabilities to these, any event in here, you can have, does 1 show, it gets 1 by 6. Yes? Does 2 show, 1 by 6. Do 1 or 2 show, that is 2 by 6. Right? So does even show, that is 1 by 2. Whatever event you make in here, then the answer, the X you get, should always satisfy this thing. Okay? What other sense should the probabilities that we assign make? Any guess?
meaning is dice ticket of इसकी probability मतलब वो 1 by 6 है इसी तरह मतलब common sense.
So we have already mentioned about X, right? So let's say you assign probabilities to, remember we assign probabilities to this, yeah? You know, क्या idea is 1 by 6, yes? Okay. Now, if I sum those, probability of 1 plus probability that 2 shows up plus probability that 3 shows up plus probability that 4 plus probability that 5 shows up plus probability that 6 shows up. Each was 1 by 6. If I sum that, what do I get? 1. Yes? What if my assigned probability somehow, it's an easy case, but you had assigned probabilities, I want to do all your elements there, and when you sum them, it wasn't 1. Maybe it was more than 1 or less than 1. Then would your assigned probabilities make sense then? Or there is something wrong? Something is wrong. Yeah, what's wrong? Your sample space is ill-defined. Either you have included things that shouldn't have been there, or you have forgotten some possibly. Let's say you have forgotten that the dice also has 6 on it. Yeah. Then what would be the क्या assign करेंगे आप इसको? Probability of 1 will be 1 by 5. Probability of 2 will be 1 by 5. But when you sum them, they won't make sense, right? तो वो क्या बनेगा 1 by यानी आपकी एक इवेंट जो probability of 6 फिर आप 0 कर रहे होंगे उसमें, yes? So if you forget some of your values or something in your sample space, that is probability. So the second logical thing is that the probability assigned to the whole sample space must be 1. Yes? So it should be not more, not less. Okay? More is wrong, less is wrong. So you are missing something there. Third one is a bit more conceptual, but I'll mention it quickly. Point, yes. Select another term. Laser है object point. Yeah, same thing. Okay, so the third logical thing is what? Probability. That is, you have already seen that, okay? Which is that mutually exclusive events should have probability 0. Okay? So there are different ways of writing it. Sometimes we write it like this, that if event E1 if event E1 intersection E2 is an empty set, that is, if there are two events that are mutually exclusive, then probability of E1 union E2 should be what? Whatever you assign, this formula should hold. What is that? Probability E1 plus probability E2. There shouldn't be any third minus term there. Yeah? So if there are any mutually exclusive events on this sample space, any mutually exclusive events, the probability assigned to their union should be the sum of their individual probability. This is another way of saying what? That this term, this thing, this should be 0. Yeah? So these are the three axioms that Kolmogorov wrote or defined, and we believe these are enough to establish probability theory mathematically. Okay, so I just call them sense check for now, which is probabilities assigned should always be between 0 and 1. Anything below or above, something is wrong. आपको लगता होगा कि जैसे how would I ever assign this? Yeah, but when you're dealing with bigger problems, you have so many probability formulas. 6 सफ़ों पे आपने solve किया, end में probability कोई भी event आप लाए थे 1.2 निकल आई. You realize either some assumption was wrong, or some calculation was wrong, or some formula that you applied was wrong, right? Because we now know that these cannot be violated. It has to be between 0 and 1. The full sample space should have probability 1, otherwise the whole thing doesn't make any sense. You are saying that this is the world of possibilities in my experiment. This is all that can happen. Then it should happen. Probability of all that can happen should be 1, should be certain. Second, thirdly, mutually exclusive events should get 0 probability. The one way of saying is to write it like this, or to say that the union should be simply a sum. The third part should disappear. Yeah? Okay. So we have now also looked at how to make sense, or say make sure that our definitions or calculations of the probabilities make sense. These are the three rules or axioms that must never be violated. You can check it on rolling a die example that we did. With that, we any questions so far, by the way? सब कुछ clear है. So you have to absorb these things, of course. Look at these again. But if you have any questions now or later, just you can ask me now or approach me in my office or email me. It's fine. I can answer you at some time. Right. So 4 important types of probabilities that we often like to talk about are joint probability. So 4 probabilities. Joint probability we already talked about, right? Briefly, लेकिन अभी हम थोड़ा डिटेल में देखेंगे. What was joint probability? 2 events happening at the same time. Another type of probability that we like to talk about is conditional. I will talk to you about that. Another one we like to talk about or use very often is posterior. क्या होता है posterior? It's the opposite of prior. Prior क्या होता है? Pehले. So फिर opposite क्या होगा? बाद. So what happens here? We will come to that. Posterior, and actually this posterior probability is the foundation of a full field of statistics and probability called Bayesian statistics, and here we will just get Bayes' theorem. Finally, there is total probability. Okay. So these 4 types, again, what are we doing? We are building your vocabulary and we are connecting those words of vocabulary to concepts. Equally likely, mutually exclusive, sample space, event, well, all those. Now these things should also add to your vocabulary. Joint probability, conditional probability, posterior probability, total probability. So what are those? Let's say it's 8 a.m. Let's say it's 8 a.m. and I define one event is that Ali is in lecture. We add me. That's good. So पहले से मैं लिखे नहीं है, so I don't want to change the name. Right. B is Ali is sleeping. Okay. So let's say it's 8 a.m. That's the experiment. We set it up, and you say, okay, A Ali is in lecture, B Ali is sleeping. 8 a.m. Yeah. So sometimes we're interested in seeing, okay, what is the likelihood of these two happening at the same time? As I mentioned, this we have already seen, and that is A and B. Probability A and B. Yes. So what would that read now? क्या मतलब होगा इसका? इस event का that at 8 a.m. Ali is sleeping in lecture. Yes. Ali is in lecture and is sleeping. Yes. So for the dice example, you could say, okay, this event that it shows even number, B it shows odd number. You could have those. That is an easy case. We saw that. What was the probability of A and B in that case? It was 0. Yes. Okay. So essentially, what we want to do is, let's see if we have this here. Yeah, we will come to that. So since we have already covered this, I won't spend too much time on this. We will come back to this again when we come to we talk about conditional now. But this is what it says. Okay, 2 things happening at the same time. I have mentioned this already. Let's say rolling a die. If A is that it shows 1, 2, or 3, and B is that it shows 2, 3, or 4. Then what is probability A and B in this case? By our base, we say, okay, so this is the size of A and B divided by the number of ways that the total S can happen. So, what is A and B? What is A and B here?
One.
Size 1, and because there is only
One.
or two and 3. Yes? So there are two common elements. So this is 2 and this is 6. Yes? 2 by 6. So probability of A and B is 1 by 3. Yeah? Now that is an easy case. Now jumping from this to the next one is the key thing. Going to conditional. Okay? That is probability. Sometimes it happens and it's very useful that knowledge of one event can help you in assigning probability to another event. Okay, so let's see that, and we will need to see, okay, how can we generalize that into a formula. By the way, this will change. How will this change? So let's say this is at 8 a.m. as I said before, and we can just write it here. We will write it like this. What's the probability that let's see if I want to do B given A or A given B in different ways. Okay, B. I want to see, okay, I tell you that Ali is in lecture at 8 a.m. Okay, I tell you this now. What do I tell you? That Ali is in lecture at 8 a.m. It's a given now. It has happened. Okay, so I say, okay, Ali is in lecture at 8 a.m. What's the probability that he's sleeping? This is different from the and one, where we were saying, what's the probability that he is in lecture and sleeping? Both things were not clear. I don't know, did he come to lecture? But now in conditional, what you do is sometimes what information you have, you add it to your calculation. So now I'm saying Ali is in lecture at 8 a.m. What's the probability he is sleeping? So that is what is given to you is now one event is given A, meaning A, I'm telling you, you can assume it has happened. He is in lecture at 8 a.m. What's the probability that he is sleeping? This is how we write it. Probability of B given A. How is it different from probability of B and A? In that both are uncertain. Here I'm telling you that B has happened. So you can assume that your world has changed. In that world, this event has already happened. And this has a symbol. This one. Most likely not. Yeah? So probability B given A. It's a conceptual jump from A and B or B and A. Yeah? It's not an and, it's a given. Here they are both uncertain. Here one thing has happened, and now you want to assign probability to the other thing. Let's play a game. Let's say I tell you that I'm going to write number from 1, 2, 3, 4. 4 numbers. One of these I write on a piece of paper. Okay? And I give it to you. But before opening, this is the experiment. Okay, na sir? Hamisha always it will start with this, setting up the experiment. Now I set up the event. What's the probability that I wrote 3? 1 over 4. What's your assumption? That I'm fair, my mind always equally likely, so usually I just want to connect it to our, as I mentioned that often in our setups we assume equally likely things, yes, so that's fine. So it is 1 over 4, yes, I tell you I wrote either 1, 2, 3 or 4, I give you the piece of paper. Before opening, your probability is 1 by 4. Now what if I tell you before you open this that I wrote an odd number? You haven't opened it yet. 1 over 2. Why? Makes sense intuitively, yes? Because now what happened? Your universe of possibilities has contracted, become smaller. Yes? So what really happened here is, in this example, this is before info, before the new info, and this is the world after the new information. Yes? Before the new information, the universe was like this, or the setup was like this. The required or the event of interest was that I wrote a 3. Yes? The sample space was 1, 2, 3, 4. So of course you had to say 1 by 4, because you're also assuming that the sample space is equally likely. Yes? So you did that, yeah? So you found that the probability of A was 1 by 4. But notice what happened once I told you that B had happened. So now the event A was 3, and I gave you an information about another event, that is that I wrote an odd number, wrote 1 or 3. Now in this case, now you are not finding probability A alone, you are finding probability A given the new information. But what happened as soon as this information showed up? What happened to S? Let's call it S new. What's the new S? 1, 2, 3, 4. These guys were obliterated. They were removed from your universe of possibilities. As soon as I told you that I wrote an odd number, the sample space shrank. Yes? Now if it shrank, you can see that A given B. Now what is the probability of A given B? Once A is B is known, what's the probability that I wrote 3 is 1 by 2. Yes? Because now this event in the new sample space is one of 2 possibilities. Yes? Equally likely possibilities. So probability A given B is 1 by 2. So it very often happens that we, in our work with statistics and probability, new information comes in and we want to use that information to pinpoint the probability better. Okay, so let's see. There is a useful formula for this also. This was, we don't always go and do this. Yeah, it will be cumbersome. ये मैंने सिर्फ आपको दिखाया to show you that this will happen. Let's see that, and then I will come into this example again. So we have a general formula that we use to calculate these things. You don't have to go into this whole thing, redefining the sample space and all that. You can often write the conditional probability in terms of what? The joint probability divided by the individual. So probability of A and B divided by probability of B. What should be the condition here for this formula to work? Mathematically सोचे थोड़े purely. There is a division. Division should always raise alarms. किससे divide नहीं करना होता? 0 से. So there is always this condition that probability for this formula to hold, probability B should not be 0. Okay, so I'll let you think about why logically, mathematically तो नजर आ रहा है for this formula to work, PB should not be 0. But logically, I'll let you think about it, why that is the case. In the case that I just showed you before, याद है वो जो example हमने discuss की थी? I wrote a number from 1 to 4. Yes. So if I apply, you already found that it was after the information, it was 1 by 2. Yeah. But let's look at it from this formula. What's probability of A and B? What's the probability that A was that I wrote 3. B is that I wrote 1 or 3. Yes. So what's the probability of A and B? Anybody can tell me? S is of course 1, 2, 3. 1 by 4. Why is that? Because A and B is just one value, 3. So total possibilities were 4. So 1 by 4. That was probability A and B, the numerator. What's the probability of B? Notice there is no given here. I haven't told you that I wrote an odd number. We're just talking about B as a general uncertain event. So what's the probability that I wrote 1 or 3? 1 over 2, because these are 2 possibilities out of 4. Now if you apply this formula, what will you do? Divide this by this. Yes. So if you divide 1 over 4 by 1 over 2, what should you get? 1 over 2. That is what you also found logically, right? That is the probability of A given B. I just applied this formula, right? Before we just calculated it logically. So what's the crux is this. Conceptually, these two are different. Here we are saying what's the probability that 2 uncertain events happen at the same time. I don't know if either of them happens or not. Right? Here I am saying I've already given you this information now that one of them has happened, which is in this case B. Now find the probability that the A will happen. So essentially this is what we use, and it's logically we can see that it will make sense. We will discuss this some more later also. Right, so a related concept to conditional probability is this. Sometimes, it's not always that the information you get is useful or related. For example, here the information you got changed the probability. What was the probability of A at first? It was 1 by 4. But once you got the information B, the probability jumped up, it changed to 1 by 2, right? But what if I give you an information with which the probability doesn't change? Okay, so what's going on in there? Information, let's say I tell you that I hand you this slip, I've written a number from 1, 2, 3, 4, yes, and before you open it, the probability of 3 is 1 by 4. Now before you open it, I give you the information that I wrote a positive integer less than 5. So let's say this is C. New information is C, that I wrote a positive integer less than 5. Yeah. So in that case, what will be probability A given C? क्या होगी? Positive integer less than 5 is 1, 2, 3, 4. Okay. So 1, 2, 3, 4. What's the probability A given C now? 1 over 2 or 1 over 4. Before you open this slip, I give you this information that I wrote a positive integer less than 5. So what's the probability that I wrote 3? 1 over 4. What was the probability that I wrote 3 before I gave you this information? by 4. So this information is useless, isn't it? Yeah. Another way, I tell you that before you open this, I tell you that I had omelette for breakfast. Okay. Does this change the probability of 3 showing or being written there? For all you know, the two have no link. Yes? So when events have no statistical bearing on each other, they are called statistically independent. This is a very important concept in probability theory. Independence. एक तो होती है ना, मुल्कों की इंडिपेंडेंस होती है, लोगों की होती है, और चीज़. This is statistical independence. Statistical independence is that knowledge of one event does not affect the probability of the other event. If that happens, we say, well, मुझे तो कोई फायदा नहीं है जानने का इस event में. Yeah, so the two are independent. There is nothing useful in this event or information of this event that will help me with the or affect my sign probabilities to this event. So there we have this. In independence, we have this. Conceptually, I just told you, but let's write how we actually also show it. It's this. If probability of A given B is the same as probability of B, and before you gave me the information, whatever probability I have assigned, after getting that information, it's the same probability, then B is basically useless in this context. Yes? Doesn't affect. Then A and B are independent. Conceptually, it is saying that when knowledge of one event does not affect the likelihood, the probability of another event, then those two events are orthogonal or independent. उसका कोई हमें फायदा नहीं है उसकी knowledge का, right? This is a very important concept of independence that we will be using later. Also, let's see if this is. So there are two tests. Just like equally likely, in most cases we assume independence. Okay? We say, yeah, there is no reason that this and this event should have any. So depending on the experiment, we realize that they are independent. For example, in rolling a die. Yes. So probability that. So I will write that down. Let me first read this one. Probability, this is one test, this is one check. Conceptually what it is, knowledge of one event does not affect the probability of the other. Mathematically this is how you write it, probability A given B is the same as probability A. This is one check. There is another way to check it is if probability of A and B turns out to be probability of A times probability of B, then we say again that this is the second check for independence. Either you will assume independence based on your intuition, just like equally likely, mutually exclusive, or you will have to prove it. When you have to prove it, you can use one of these two. This one is directly from the concept of independence. But this one, we can't say second one. So we wrote a formula for A given B. What was it? Given that B is not 0. Yeah? Okay. So if you look at that, and can I rewrite this formula like this? Probability A intersection B is probability A given B times probability B. I can write it? Yes? Now look at the first condition. If the two are independent, The first condition or the first check says that this should be P, A, yes, which leads to the second test. So the two are equivalent. If one happens, the other will also happen. Yeah. So probability of A intersection B is PA times PB. We like to say that if the joint probability is separable. In general, it is not. In general, the joint probability is like this: probability A intersection B times probability B. But if it turns out to be simply PA times PB, we say that the two are independent. So these are two checks, two tests that you can apply to this to test independence. Questions on independence? Subhadar? Yes? So remember, we are developing the concept. You will maybe get it now, but you will also forget it very soon. Yeah, there's a lot of concepts. You really have to lock them somewhere. Sheet लेके उस पे एक term and then writing the concept and the relative formula. रटा नहीं लगाना उसका, लेकिन you have to help your mind collect the useful information. Many of you do what you say, yeah, it's there in the book. Book में पता कितने सफ़े हैं? यदि आपकी बुक में 800 सफ़ों की है, right? Can your mind keep that track of that? Yeah. Lecture, okay. Lecture slides कितनी होगी? This is many hours of lecture. Can your mind keep track of that? You say we look at the slides, doesn't help. Summarize करेगा. If you don't do that, believe me, all of this will be too much to handle eventually. Okay? So start locking, start collecting the key words and the key terms. Right, so we have talked about now which probabilities? Joint, conditional. And from conditional we developed the concept of independence. Yes? So independence is where conditional doesn't help. Doesn't matter. और मैंने क्या बताई थी? Posterior and total. Yes? So let's talk about very quickly. Let's say there is a system, in a factory there is a machine or a system that has two distinct components, two distinct parts. Alpha, I label one alpha, the other beta. Yeah? And the probability that alpha fails is 0.01. Yes? So at any given time, so a machine has two distinct parts, alpha and beta. The probability that alpha fails is 0.01. Probability that beta fails is whatever number I have here, doesn't really matter, but it's the same. 0.005. And probability that beta fails if alpha has failed is 0.015. So there are two components in the machine, different. One of them failing, alpha की probability है 0.01. Other one failing 0.05. And we also know from our collected data about that machine that we know that when alpha fails, if alpha has failed, then the chances of beta failing become 0.015. Now, the question we may be interested in asking in many situations is the reverse of this. That what is the probability that alpha will fail if beta has failed? What happened here? Switch kar diya. Yeah? You have information about these, but I'm interested in something else now. Can I find this from what I have, or should I again collect a lot of data? Smart people, if you can find some way to solve this, you don't need to collect more data. This is if it is already Here, first of all, which component is more reliable by the way? इस machine का कौन सा component ज़्यादा mechanical से कौन है? Yeah. कौन सा component ज़्यादा reliable है इस machine का? Beta ज़्यादा reliable है. Because its probability of failing is very low. Good. Are the two events independent? Based on this information. Are the beta and alpha failing? Are the two events are they independent of each other? Or does one knowledge of one affect the other? Answer is here. Probability of B before I tell you anything about alpha failing is this. But probability of beta failing once I know that alpha has failed, is it the same or has it changed? So, probability of beta given alpha, is it the same as the probability of beta before you knew about alpha failing? No? Yes? There are different values here. So from here you can already guess that they are dependent. होता ये होगा ना कि एक फेल होता है दूसरे पे लोड बढ़ जाता है उसको गलत फ्यूल जाता है तो वो भी सड़ जाता है. Right? So they are dependent. You don't have to know the machine in this case. Just from the values here you can tell, yeah, this is violated. Yes? So they are dependent, that's fine. But what about now this question that probability A given B. Okay, so let's look at this this way. What are we asking for? Are we asking for? So we have probability of alpha is 0.01. Probability of beta is 0.005, and this is probability beta given alpha. And what we are asking for is probability alpha given beta. I'm assuming this is saying alpha fails. Yes? So equals +1. Can we find this from this information? What do you think? Do we have some formula that could help us? So what is probability alpha given beta? By the formula that we just saw. I'll help you. It's alpha and beta divided by beta. Now there is a problem. What is the problem? Do I have probability beta? Yes. Do I have probability alpha and beta? No. What do I do? कुछ कर सकते हैं आप इसका? What is probability beta given alpha? Do I have this? Yes? I can write it like this. Probability of alpha and beta divided by probability of alpha. Can I write it like this?
Yes.
I can? Good. Do I have this?
Are they both commutative?
ये तो होता है ये नहीं हो नहीं वो नहीं you can see from here the denominator different than numerator same है. Yes, so they are not definitely not commutative. Yeah. So but notice, do we have this? Yes. Do we have this? Yes. What was missing in this formula? The numerator. So now you have the numerator. No? It doesn't valid. So it's what? Probability beta given alpha times probability alpha. So I'm going to write it here like that. I can write it. What can I write? Probability beta given alpha times probability alpha divided by probability beta. Agreed? Now I can solve or no? Without collecting the statistics again, I can tell you the reverse of this also. Yeah. So you give me probability beta given alpha, and the individual probabilities I can tell you probability alpha given beta. But it's not just this problem. It's just this formula that I want you to look at. So which formula? This to this. Okay. Forget this for a while. It's a very beautiful result. It's a whole branch of statistics and probability called Bayesian statistics and Bayesian probability. You will hear of Bayesian neural networks tomorrow when you study some part of data science or machine learning. The idea is a very interesting concept. Firstly, notice that what are you doing? Whose probability are you finding? Of alpha failing. Yes? When an event has occurred. What's the event? Beta. Event has occurred. What is this probability? If this guy will fail in general. Yes? So what we are doing is we are going from non-conditional probability of alpha to a conditional probability of alpha. This one we call prior probability. Probability that we knew before information of an event came in. Yes? Once the information of an event comes in, we update this using this formula and reach a posterior. Prior was before and posterior is after. Before the new information comes in that beta has failed, this is the probability of alpha failing. Now you want to update that probability using knowledge of the event. So this is a very powerful formula that helps you do that. Okay, and this is also the one way of solving problems where you start with your neural networks. You know what it does, neural network, when it's starting. पहली cat की तस्वीर आई इसको. So it starts with something very random. Yeah. So it says what's the probability that it's a cat? 50%. Cycle भी दे देंगे ना उसको पहली दफा. जब वो train होगा. Of course once it's trained it knows. The chat GPT you have worked with is trained already, so it knows. But before it is trained, if you give it a cycle or a cat, it will say, yeah, 50% chance it is, 50% it is not. What it does then information comes in. Okay, I'm going to give you a picture, and it is a cat. This is new information. Then I'm going to give you another picture. It is also a cat. I'm going to give you another picture. It is a cycle. It's not a cat. So every time your algorithm is constantly bringing in new information, it starts with a prior and then it's training itself. जो आप पढ़ते हैं ना ट्रेन के बाद ट्रेन conceptually really this is what's happening. उसके डिजाइन उसकी extensions हैं. But this is what's happening in concept. You start with a prior basic initial assumption and then you improve on your probabilities with time with your you work with this assessments. So this thing we call also Bayes theorem. Okay, so I'll write that and we will close today's lecture. Bayes theorem basically says that if you have the prior probability of an event A and you want to update it once you have new information. Yeah, what's the problem with starting from the scratch? So you've been training your neural network that is a cat, Now a new picture of a cat comes. Should it start from the very first value or should it add to its previous knowledge? Yeah. So you always want to add to your previous knowledge. So whatever you currently know, you want to now include some new information. So you want to go from prior to posterior. And this is the Bayes theorem that is going to help you do it. It says, okay, it is probability of B given A divided by probability of B. Of course, you have to know these. Yeah? And in these kinds of applications, we actually know these things. We already calculate those. So this gives you an opportunity for what? An iterative update. Yeah? So next time this becomes your probability of A or whatever new event you are, and then you update that with another new information. New data comes in. You keep doing it in cycles and you keep improving these probabilities or making them more precise. Okay? So I also wanted to do total probability today, but I think we will be totally lost by and then. So we'll do that next time. We talked about joint, conditional, posterior. Yeah. With posterior, we also saw prior probability, posterior probability. One left, that is total. Yeah. So next time we do that, and then we jump to random variables, from events to variables. Yeah. Okay.